Hi, I'm Bulbul Rath and today I'm going to discuss about the project topic that is analysis of V-blast detection method in MIMO systems for enhanced system performance. Firstly, we'll go over the topics we're going to cover in this entire PPT. Firstly, we'll go over the architecture of V-blast, thereafter the detection algorithm. Then we'll go through the different types of detectors like zero forcing, minimum mean square error, maximum likelihood, zero forcing on MMSC both with ordered successive interference cancellation. We'll go into the analysis of each of these detectors and we'll go over the simulation and results. Now, what is V-blast? The MIMO systems have actually been introduced in order to efficiently increase system capacity with the rapid advances in wireless communications. Multiple antennae at transmitter and receiver help enhance system capacity, increase throughput, and improve link reliability. V-blast is basically the famous Bell Labs layered spacetime coding. This is a vertical type of coding, vertical layering, and therefore it's called vertical V-blast or vertical Bell Labs layered spacetime coding. It is a transceiver architecture developed in MIMO receivers, and it basically employs spatial multiplexing. This is the architecture of the entire V-blast system. You have the transmitter, you have the receiver, you have transmitter antennae, you have the receiver antennae. And here you see you have your entire transmitter system, you have your entire receiver system. Your transmitter data comes in, then it goes into the different transmitter antennae into different substreams, then it goes into and is collected by the receiver at the receiver end. At the receiver end, you employ the V-blast in order to make the detection of the or the estimate of the transmitted symbols at the receiver. Now, the architecture consists here of M transmitted antennae and N receiver antennae. The architecture in details. You have M transmitters which operate at a symbol rate of 1 by T. You also have N receivers and they operate co-channel. Each of the receiver receives a superposition of faded signals. The channel is basically assumed to be exhibiting flat fading. Now, high spectral efficiency can be achieved by using spatial multiplexing, or spatially multiplexing coded and uncoded both types of symbols over the MIMO channel, and this is employed by the V-blast technique. Now, the V-blast detector makes a decision based on the set of symbols which are closest in Euclidean distance to the received symbols. So, out of all the possible combinations of estimated transmitted symbols, you pick up the ones which are closest in Euclidean distance to the received symbols. Next, we go on into the detection algorithm. The incoming data stream at the transmitter is divided into M substreams known as layers. They are arranged horizontally across space and time. Now, the detection process consists of two steps. One, interference suppression, and second, interference cancellation. What is interference suppression or nulling? Basically, it is used to remove interference so that a proper or a correct and accurate detection can be made. So for this purpose, what you need to do is, the received vector needs to be projected onto perpendicular subspace spanned by interfering signals. Now because it is a perpendicular subspace for the interfering signals, so the received vector will not be affected by interference. So this basically removes interference and detection can be performed. When you have interference cancellation or subtraction, here the detected symbol is then subtracted from the received vector. Okay, so for this purpose, what you do is each time you get a new detected symbol, you subtract it from the received vector and modify it to produce a new vector. We'll go about it in details in the next slide. Next, you have the mathematical explanation of the entire algorithm. Considering that you have a channel function given by matrix H of n rows and m columns, the element Hij is the transfer function from the transmitter J to receiver I, and your number of transmitter antennae is either less than or equal to the number of receiver antennae. So n less than equal to n. Your transmitted vector of length m can be given as a vector A, given as elements of A1 to Am. Then your received vector is given from the channel matrix as HA. That is the channel matrix multiplied by the transmitted vector. And you have an additive noise vector or a WSS noise vector. Then you have your expected set of symbols at receiver. This is very important. This helps you to make your detection. Your S vector is the possible combination of expected set of symbols at the receiver. your y vector will be a decision parameter. So basically we need to have a decision parameter in order to make an estimate of the type of transmitted symbols we actually receive as the receiver. So this y is a decision parameter used to enable to make the detection. And finally, your interference nulling and cancellation methods that we discussed in the last slide are used to calculate y. Because based on y, you make the estimate of the transmitted vector A. Okay, so this nulling vector y, W1, is used to calculate decision vector using received vector R1. You have a nulling vector called W1. Now this is used to perform the interference nulling. It is used to calculate the decision vector y, yk1, using the received vector R1. So yk1 is W1 transpose R1. So then you y1, you have a slicing operation performed on y1 or the decision parameter in order to obtain an estimate of the transmitted vector or a1k1 as follows. So if ak1 is your transmitted vector, a1k1 would be its estimate. Now this slicing operation q that is shown here is an operation depending on the type of constellation you have, a number of symbols are being employed based on the type of modulation. For instance, if you use QAM or if you use QP escape, depending on that. Then you have your estimate a1k1, and we make an assumption that it will be equal to the actual transmitted vector. So based on this assumption, we subtract it or cancel it out or eliminate it from the received vector and get a new received vector R2. So basically these are the key generic steps of BLAST algorithm. First step, finding the nulling vector and then making the decision parameter. From the decision parameter, we obtain the estimate of the transmitted vector A, and we perform a slicing operation to do that. And thirdly, we subtract this estimate from the received vector. Now these steps will be performed in recursion for all the elements of the expected vector S to obtain modified received vectors R3, R4 and so on. So this is the generic part. Now based on the type of detectors used, you have specific algorithms which are going to be discussed in the next slides. There are different types of detectors that are used in BLAST, like zero forcing, MMSE, a minimum mean square error, maximum likelihood, etc. You also have STBC and like, but here we'll be concentrating on the most commonly used ones like zero forcing, MMSE and maximum likelihood. First we go on to the zero forcing technique. Now in zero forcing, nulling vector is actually defined as the minimum norm vector defined by WKI transpose H of Kj is 0 for j greater than I and 1 for j equals to I. So as we recall, we had just seen that I just told you that the detecting of the decision parameter is done on the basis of your, as you can see in this slide, your decision parameter is detected from a nulling vector. So this nulling vector is obtained from the basis of the type of detectors you use. In case of zero forcing, this is the nulling vector definition that we use. Now, the noise power of the decision statistic y is proportional to this nulling vector, and so later we will find that the SNRs also will be proportional to the nulling vector, but the norm of the nulling vector. The full zero forcing algorithm is a recursive procedure because it will be performed again and again for every element and outlined as follows. Firstly, you initialize the iteration value I equals to 1, and then you have a channel matrix given as the pseudo inverse of the actual channel matrix H plus. So you have the recursion algorithm as follows. These steps are going to be performed again and again for every element. Now firstly you calculate the estimate, that is S vector elements from Ki equals to argument minimum value of this Gij norm, that is determines optimal S vector. And the condition is the value of J here is not an element from K1 to Ki minus 1. Next you determine the nulling vector. For determining nulling vector you do the operation of the channel matrix Gi into Ki, that is the optimal S vector element. On obtaining this decision vector, you will then perform the calculation to find the decision parameter. First we find the nulling vector, then we get the decision parameter y from the nulling vector as discussed in the last equations. So here you see that yki is equal to wki transpose ri, that is received vector and nulling vector. Then the estimate of the transmitted vector would be made from the decision parameter by splicing it, that is q of yki. And lastly you get the elimination of this particular estimate from the received vector. So you have a new received vector ri plus 1, which is the old one ri subtracted with the estimate of the transmitted vector. Then you change your channel matrix to H1 Ki plus, that is new pseudo inverse, and you increase the iteration value to go on to the next iteration. Now that was the zero forcing technique. We have another technique called minimum mean square error, which we also use in BLAST. In this type of detector, you change your filter matrix. It is given as your Hermitian matrix of the channel matrix H multiplied by the channel matrix H, plus you have a sigma square, and this is your INR, that is identity matrix, and this whole thing is taken to be the inverse, and then you have your channel matrix again with its Hermitian value. So this is the definition for the channel matrix which you employ for the MMSE detector. Now, contrary to zero forcing, which only eliminates interference, your minimum mean square error helps in removing interference as well as noise, and it has a simple linear receiver, that is one of its advantages. Now, on the basis of this channel matrix, you have a filter output given as SMMSE is equal to your transmitted vector into a filter matrix. So this is your final value. Now, if you extend your H1 and X1 to obtain these new matrices given by these definitions here, you will see that the output of MMSE filter becomes H1 pseudo inverse X. And thereafter, the entire recursion method is similar to what is being deployed in zero forcing. So the only difference comes in defining G here, initial G channel matrix. Then you have maximum likelihood. It's one of the best methods to be implemented, but because of its high complexity in setting up a receiver, it's still having problems. And how is it used? It is used for vector decoding, and it is highly instrumental in reducing probability of error. It has a very good bit rate performance, as we will see later when we perform the simulations about it. Then you have received signals are compared with possible combinations of transmitted signal vector, that is the estimate. The transmitted signal vector is obtained from channel matrix H. The estimate of transmitted signal vector here, you directly have your estimate of transmitted signal vector. You don't have to calculate decision parameter and all. You take argument minimum value of r minus hxk square. R is a received vector. Xk belongs to x1 to xn. The error reduction is performed over all possible estimates of transmitted A vector. Okay, so this is also a recursion method once this particular step is accomplished. So then you have VBLAST with zero forcing and MMSE with OSIC, or ordered successive interference cancellation. So it's explained as follows. Now, firstly, this is employed because it has efficient interference reduction, as the name suggests, ordered successive interference cancellation for both zero forcing and MMSE, so it improves performance in both cases. Now you have your initialization again, I is 1. You have a channel matrix defined Gi as pseudo inverse of H by Gi. Then you have this final value. Then you have the recursion algorithm as described before. You find the optimal S vector Ki, then you find your nulling vector Wki, then you find the decision parameter, then you find the estimated transmitted vector, and you find the new received vector by subtraction or removal of the estimated vector. Then you find the new channel matrix and you increase the iteration value. Now we'll go over to simulating our code. So, firstly, we have implemented BLAST algorithm in a MIMO of second order, and we have used QPSK modulation in it, and we performed this for all the different types of detectors like maximum likelihood, then MMSE, zero forcing, and MMSE and zero forcing with OSIC. So, as you can see here, the order of the MIMO is defined here, transmitter antenna 2, receiver antenna 2. Then you have your frame length, that is number of data which is going to be coming in. You have range of your SNR here from 0 to 12, and we will perform the algorithm for all of them so that we can get a performance of the bit rate for different values of EB by N0. Thereafter, you have your AWG and noise being added. Then you will start performing each of the algorithms from here. First, you have maximum likelihood. We perform the vector decoding in this particular loop here, taking each of the values from the transmitter and then performing the calculations. And then you have your zero forcing technique, where again you take the transmitter, find the estimate, and similarly for MMSE. Then you have zero forcing with OSIC, that is the interference cancellation, and MMSE with OSIC. As you can see, we have calculated a pseudo inverse here, and you're calculating the entire G matrix, iterating the value, subtracting the receiver, and from with the new value. Also, in maximum likelihood here, you can see that the new receiver value has been found out by subtracting the old estimate. And lastly, we have MMSE with OSIC. So I'll go ahead and run the simulation, and we'll wait for the results. As you can see here, the values are being printed for each of the arrays that are going to be stored with the error probability, and then we'll have the final output of the simulation. Here we get it now. Okay, now what do we conclude from the simulation? Here on the left hand side, the y-axis is the bit error performance or error probability, and the x-axis is EB by N0. This black curve corresponds to maximum likelihood. So as you can see, the maximum likelihood gives the best BER performance, and the zero forcing, which is the red curve, gives the worst performance. There is a kind of trade-off between the pink curve and the green curve, that is ZF plus OSIC and MMSE, but generally speaking, MMSE performs much better. And if you make changes in the order and changes in modulation, this difference will be stark clear. So we see that the bit error performance is the best achieved in maximum likelihood, and followed by MMSE with ordered successive interference cancellation, followed by zero forcing with ordered successive interference cancellation, and then you have your MMSE, and lastly your zero forcing. MMSE actually performs better work than zero forcing because it removes noise and interference both, and hence it is a better bit error rate performance. However, maximum likelihood is the best, but because of receiver complexity, we move on to zero forcing and MMSE. Okay, now we have another simulation which I have implemented using QAM. We have a 16 QAM modulation employed in a fourth order MIMO, and the same study has been made, but we have not put maximum likelihood here. Mainly, we're trying to see the difference in zero forcing and MMSE with a higher order modulation, higher order MIMO. So it's the same code basically. So it's just transmitter antenna 4, receiver antenna 4. So fourth order MIMO. I simulate this, and here I see that I have again the best bit error rate performance for MMSE with OSIC, followed by ZF plus OSIC, followed by MMSE, and followed by zero forcing. So everywhere, wherever MMSE occurs, it will provide a much better bit error rate performance. Because it suppresses noise, it achieves a trade-off between interference, cancellation, and noise enhancement. I also have made a study between the different types of orders of MIMO for the same type of modulation and the same technique. Say here we have zero forcing technique, but we have two MIMOs of order 2 by 2 and 4 by 4, and we have QPSK modulation. So if I run this, you see that as the order increases, the bit error rate becomes lesser. So you have a better bit error rate performance for 2 by 2 MIMO, and the bit error rate kind of decreases with a 4 by 4 MIMO. Similarly, you have your MMSE. Same result is obtained here too. So now we'll go back to our simulation results. You can see the final results. As I said, maximum likelihood is the best bit error rate performance. And same for QAM modulation. This is for different orders of MIMO. You have low order MIMO giving a better bit error rate performance. So the final results will be discussed. The maximum likelihood vector provides best BER performance, but it has an exponential increase in complexity architecture, so its implementation is difficult. You have MMSE with OSIC. It provides good bit error rate performance. It minimizes interference with much less noise enhancement. You have zero forcing with OSIC. It shows comparatively good bit error rate if you compare it only with zero forcing, and slightly more from MMSE, but it still has a long way to go. Then you have the MMSE detector. It provides noise and interference cancellation as compared to zero forcing, which only eliminates interference. Hence, ZF provides low BER performance. And lastly, you have MIMO increases BER performance for a given detection method also kind of becomes lesser. You have analysis of detection methods. Now, zero forcing, it is used in reblast in order to reduce receiver complexity. It increases noise as well while it suppresses interference. MMSC helps in reducing noise and interference both, hence it is superior to ZF. At low SNR, it acts like a matched filter. At high SNR, it approaches ZF. Maximum likelihood, high receiver complexity, hence it is difficult to implement. Zero forcing with OSIC, it suppresses intersymbol interference completely, but it cannot suppress noise. MMSC with OSIC achieves a trade-off between noise increase and interference elimination. So that's the entire analysis of all the different types of detectors in VBLAST. So finally, we'll conclude. VBLAST is a very efficient technique of increasing system capacity in MIMO. We have made we've come across different types of detectors which are used in VBLAST to improve its performance in this particular project. VBLAST can help to channel the data to a higher data rate when coupled with MIMO. And you have your trade-offs based on cost, availability, architecture setup, signal to noise ratio, error probability, and interference effects. VBLAST architecture has still a long way to go. It has a scope of higher improvement wherein it can actually achieve very high throughput and capacity, and it can be made to achieve error-free detection in the MIMO receiver. So that's it from me. Thank you.